All right, we're back. So previously we talked about Newton's second law and how an acceleration changes. If you increase the force, the acceleration gets bigger. If you increase the mass, your acceleration would get smaller. Using n-2, that's going to stand for Newton's second law. The net force equals the stuff that makes it go minus the stuff holding it back, equals mass times acceleration. We need to be able to use Newton's second law to solve problems dealing with forces. How do you know when to use this? When do you use kinematics? When do you use conservation of energy? We're going to use forces and these strategies that we're going to talk about whenever we're analyzing forces acting on objects. First things first, we're going to draw those free body diagrams. It's been a little while, right? But we remember it just starts with a dot. Gravity always goes down, and then we label it. Then we deal with the other forces. If there's a normal force, a tension force, an applied force, whatever it is, we have to represent it with an arrow that is the correct size. Next, we're going to use the free body diagram to write an equation, creating our own equation. 3, solve the equation for whatever the unknown is for. Whatever the unknown is. Here we go. There's the Friendly Physics logo, taken from Aperture Science, whatever. Basic example. A student pulls on a 10-kilogram box with a horizontal rope. The rope exerts 100 newtons of force to the right, but there is also 80 newtons of friction force to the left. What is the acceleration of the sled? Before I go on with the PowerPoint, I'm going to go through that first method that I showed you so that way you can get different ideas on how to solve this. So remember I said the stuff that makes it go. So our net force, F net, equals stuff that makes it go minus stuff that holds it back, equals mass times acceleration. And that acceleration is our net acceleration. So what is making this go? Well, first thing, we're going to start with a free body diagram, which is just a dot. Let's go ahead and make this dot a little bit bigger. We have a 10-kilogram box, so there's definitely a weight force here, which we'll call F sub W. Then we have a horizontal rope. The rope we got to have a normal force. It's got to be balanced, because if I didn't have it balanced, that would tell me this box is sinking down into the ground pretty quickly. So these two forces cancel each other out. Then we have 100 newtons of tension force to the right. We'll call that Ft. Here, hold. Oh, come on. Don't give up on it. There we go. FF. So there we go. Now, if we look, we have to look at our forces separately. We have our vertical forces and we have our horizontal forces. I feel like this should be vertical forces, but that's all right. It's the same process. So in the vertical direction, we can call it a net force in the y direction. The stuff that makes it go up, because that's our positive, minus stuff holding it back, Fw, equals mass times acceleration. Well, what's our acceleration? It's 0, because it's not moving. So now I'm going to go through and I'm going to look at it in the horizontal, in the x direction. And the key here is you have to treat x and y completely separately. So we're looking in the x direction. Stuff that makes it go, in this case, tension is winning, minus the stuff holding it back, frictional force. Whatever that is going to be equal mass times acceleration. And we're looking for acceleration. So our tension force is 100 newtons, minus our frictional force, 80 newtons, equals mass, which is 10, times acceleration. So we get 20 divided by 10, acceleration is 2 meters per second squared. Okay, that's the first way. On to the second way. Giving you multiple looks at it, so that way you can pick one that works best for you. All right, step 1, draw a free body diagram. Weight, normal force cancel each other out. Tension is slightly bigger than our frictional force. Slightly bigger. kind of hard to see bigger. Next, step 2, create Newton's second law equation and solve. F net equals mass times acceleration. The up and down forces balance, so we're not going to include them. We can just say, oh yes, that thing is not moving up, that thing's not moving down. We don't care about what's happening in the y direction. Still represented on your free body diagram, but we don't have to do any calculations with it. Right force is tension, left force is friction. So we're adding together these forces. Stuff that makes it go minus stuff that holds back, or Ft minus Ff equals ma. And we still get the 2 meters per second squared. So the difference here, it looks pretty similar. The difference is not, with the first way, you don't care about what is positive and what is negative. With the second method, to the right is positive and to the left is negative. Free fall. Why do objects fall at the same rate? Because the only force acting on them is gravity. Step 1, draw a free body diagram of this thing. Write Newton's second law equation. The net force, stuff that makes it go minus stuff that holds it back, equals mass times acceleration. The only force is the weight, so mg equals ma. Mass cancels out because we have mass on each side, so acceleration equals gravitational acceleration, or the gravitational field. And all objects fall with the same acceleration within that gravitational field. Rest of the lesson is going to be examples. Each example is important, so take your time with them. Breaking strength of a cable lifting a box, scale reading in an elevator, measuring the acceleration of an elevator, skydiver falling, and opening a parachute. These are all very classic physics problems that show pretty really in some form or another. So we're going to go through those in the next